question 1 shows two simple harmonic oscillators. These are masses attached to springs. And we just want to compare the harmonic oscillators and see what we can tell about perhaps their frequency and period. So it says setup 1 is made up of mass hanging from a spring of length L, but setup 2 has the same mass hanging from 3 identical springs of length L, where the total length is 3L, so it's a longer spring, but the same material, same everything. Okay, then it says you're going to pull these down by 8 centimeters and release. How do you believe the period, frequency, and amplitude of setup 2 compares to setup 1? So choices are, do you think the frequency would be larger? Would the period be larger? And also, would the amplitude be larger? So I'm going to give a physics explanation of the answer. I'm going to analyze it according to Newton's laws. Alright, so according to Newton's laws, we can draw a diagram for the mass. So we have one mass hanging. Now he has a weight, which is a vertical force of gravity pulling him down. And so in order for him to right now be in equilibrium, the spring has to pull up with the same force. I'll call it Fs for force of spring. Okay, then in addition to that mass, we have our other mass who is the same weight. So he's got the same Fg as the other one. And the force of the spring, therefore, according to Newton's laws, must currently be the same for both springs. Okay, however, one of the springs has a short length. The other one, much longer, 3 times longer. Okay, so when a spring is able to exert a force like that, we would use a formula for the spring constant. And the spring constant is K equals your force divided by your length. So I'll ask you, which mass here has the larger K and which one has the smaller K? Let's just put some numbers to it. Let's say that one spring is like 1 kilogram and 1 meter. Then on the other one, we've got 1 kilogram and 3 meters. If we were to do a sample calculation of their spring constants, the one would have a K equal to the force, which is the mass times G divided by your length. So the force comes from a weight formula, W equals mg. So each of these hanging masses has a weight of 9.8 newtons. Because it's 9.8 newtons per kilogram, that's G, and they're each 1 kilogram, therefore they each weigh 9.8 newtons. So for our first spring, he's going to be 9.8 newtons divided by 1 meter. For our other K, K2 I'll call it, it's going to be 9.8 newtons divided by 3 meters, which is a K of about 3.3. Okay, so one of them is stiffer than the other. I'll ask you, which spring would be considered in physics stiffer? The 1 meter spring or the 3 meter? Yeah, exactly. Spring constant tells you about the stiffness. Okay, now when you think of like a stiff spring, do you think the oscillation is going to be like having a higher frequency or a lower frequency or the same as the 3 meter? Then what about their periods? Which one has the longer period? So yeah, that answers that. We'll check the boxes. You got to put that the frequency of setup 2 will be lower. The period of setup 2 would be longer. And also the amplitudes of them would be the same. It also asks for a specific amplitude for setup 2. So because you pull it down by 8 centimeters, it's actually going to be 8 centimeters. Yeah. In fact, we can calculate perhaps some of the things. There's a formula for period of a harmonic oscillator. We'll try to calculate what the period is going to be. This is the formula for it. So we can now apply that to both of our masses. So for the short spring versus the long, you'll have 2 pi square root of 1 kilogram over 9.8 newtons per meter. That was the spring constant that we had found. The period of the long spring will be this. Let's see what they would be so that we can graph it. I get 2 seconds for the short spring, and then let's do it for the long spring. We get 3.5 seconds. Okay, now that we have that, we can find their frequencies too, just by doing 1 over their periods. So this one's a 0.5 hertz frequency, whereas the other one is 0.29 hertz. So then if we wanted to plot these as waves in Desmos, we could simply use the general form of a harmonic oscillator, which is going to be y equals a sine of 2 pi f t. We could do that for both. So let's put in our amplitude. Is going to be 8 centimeters. Put in your frequency, 0.5, and then your letter T. The other one will also have an 8 centimeter amplitude. And we'll put in his frequency. And they can now be plotted in Desmos. So here's spring 1. And here is spring 2. If we change the view, we could zoom in a little. And we see that they have the same amplitude. Okay, so same height of the wave. But they have different frequencies and periods. Clearly, the one with the stiffer constant is more compressed. The one with the smaller spring constant, obviously more stretched out.